An engine can start every morning, idle smoothly, and pull down the road and still be wearing itself out from the inside. That's what misleads most drivers. We're taught to judge engine health by obvious signs, warning lights, noises, smoke. But modern engines are designed to hide problems. Computers compensate, sensors adapt, small losses get corrected quietly. And while everything feels normal, heat, pressure, and contamination are slowly changing how the engine works. You don't have to take my word for it. Real-world behavior shows it too. A recent survey found that 69% of drivers delay maintenance even after knowing it's due, and 64% are currently putting off some form of vehicle servicing, meaning most people let issues linger until they get worse. Engines rarely fail all at once. They don't collapse overnight. They fade. Power drops a little. Efficiency slips. Stress builds where you can't see it. By the time something feels wrong, the damage has often been happening for years. If you want to catch problems while they're still invisible, following along will help you see what most drivers miss. And once you understand how engines fade, the real damage becomes easier to see. How engines quietly age from the inside. Engines don't wear out because of birthdays. They age because of repetition. Every drive creates heat. Every shutdown traps moisture. Every restart changes pressure inside the block. Over time, those cycles leave traces behind, not all at once, and not in ways you can easily feel from the driver's seat. Heat expands metal. Cooling contracts it. Oil thins when hot and thickens when cold. Combustion creates gases that don't all escape cleanly. None of this is harmful by itself. Engines are built for it. The problem is accumulation. Tiny inefficiencies that seem harmless on their own begin stacking. A little extra heat here, slightly slower flow there, a bit more residue left behind after shutdown. Modern engines are especially good at hiding this process. Computers adjust timing. Fuel delivery adapts. Idle smooths itself out. So instead of alerting you, the engine compensates, and compensation feels like normal operation. That's why many engines feel fine right up until the moment they don't. This is why age alone is rarely the cause of failure. Two engines with the same mileage can be in completely different condition depending on how those internal stresses were managed over time. The real story isn't how old the engine is, it's how long it's been quietly working around growing resistance. And the first place engines begin to suffer is somewhere most people never think to look. When airflow stops telling the truth. Engines don't just need air, they need to know exactly how much air is coming in. Power, efficiency, and engine safety all depend on accurate airflow information. When that information starts drifting, the engine doesn't panic, it guesses. Airflow problems rarely start with blockage. They begin with subtle misreading. Small changes in intake flow, surface buildup, or turbulence can affect how air moves past sensors. The engine still breathes, but the data feeding the computer becomes slightly less precise. That loss of accuracy doesn't trigger a warning. It triggers correction. The computer responds by adjusting fuel, timing, and throttle behavior to keep things stable. From the driver's perspective, nothing seems broken. From the engine's perspective, it's now working harder to achieve the same result. That extra effort shows up as heat, strain, and slower response over time. This is why airflow-related issues almost never feel sudden. They develop gradually. Throttle response softens. Acceleration feels muted. Fuel economy slips just enough to be ignored. The engine isn't failing, it's compensating. And once airflow data is slightly off, every other system starts adjusting around it. Not because something is wrong, but because the engine is trying to protect itself. Because once airflow data is wrong, everything else starts compensating. The slow suffocation that feels like lost power. When drivers complain about lost power, they usually describe it the same way. The car feels heavier. Acceleration isn't sharp anymore. Merging takes more pedal. Nothing dramatic, just dull. Most assume that's age. Or weight. Or that's just how it is now. What's actually happening is far quieter. As airflow accuracy drops, the engine reduces how aggressively it responds. Throttle input doesn't translate into the same immediate movement. Timing shifts slightly to stay safe. Fuel delivery smooths out to avoid instability. The engine adapts instead of alerting. That adaptation feels like normal driving, until you compare it to how the car used to respond. And because there's no single failure point, nothing gets blamed. No warning light, No obvious noise. Just gradual suffocation. The engine can still breathe, but not freely, and not confidently. Over time, this restriction creates stress. The engine runs warmer under load. Combustion becomes less efficient. Deposits form more easily. What began as a small airflow issue slowly turns into a system-wide strain. This is why restoring airflow often feels like giving the engine its voice back. Not because something was broken, but because the engine no longer has to hold itself back to stay stable. But air alone doesn't create power. The fuel system has to keep up. Why fuel stops burning the way it used to? For fuel to burn efficiently, it has to arrive as a fine mist. That mist mixes evenly with air, ignites cleanly, and releases energy smoothly. When that spray pattern changes, combustion still happens, just not as well. Over time, fuel delivery components experience heat soak. After shutdown, residual fuel sits in hot areas and slowly changes. Tiny deposits form, spray patterns lose their sharpness. Instead of a uniform mist, fuel begins entering the engine in uneven streams. The engine doesn't misfire, it doesn't stall, it simply burns less cleanly. That incomplete combustion wastes energy and creates extra heat. It leaves behind more residue, and it forces the engine computer to keep adjusting, trying to balance a process that's no longer precise. Fuel economy drops, throttle response softens, emissions rise quietly. The dangerous part is how normal this feels. There's no dramatic failure, no sudden breakdown, just gradual inefficiency that becomes the new baseline. Drivers adapt their expectations the same way engines adapt their behavior. And as combustion quality declines, the computer works harder to correct something it can't directly measure, setting the stage for even more hidden strain. And when combustion quality drops, the computer tries to fix something it can't see. Quick pause. If avoiding costly engine problems matters to you, consider subscribing. The sensors that drift without warning lights. Modern engines don't make decisions based on sound, feel, or instinct. They operate entirely on data. Every second the engine is running, sensors report airflow, exhaust composition, temperature, engine load, and operating conditions to the computer. That data determines how much fuel is injected, when the spark fires, and how aggressively the engine responds. The computer doesn't question those signals. It assumes they're telling the truth. The issue is that most sensors don't fail in an obvious way. They don't shut off suddenly or trigger an immediate warning light. Instead, they age. Repeated heat cycles slowly reduce response speed. Constant exposure to exhaust gases dulls sensitivity. Vibration affects how precisely signals are read. Over time, the numbers drift, not enough to be flagged as a fault, but enough to matter. When readings drift, the computer doesn't alert the driver. It compensates. Fuel trims adjust slightly to maintain smooth operation. Timing is softened to avoid instability. Throttle response becomes more conservative. From the driver's seat, the engine feels normal, sometimes even smoother than before. That's the trap. Behind the scenes, combustion becomes less precise. A little extra fuel is used. A little more heat is generated. Efficiency drops quietly. These small changes don't cause immediate problems, but they increase long-term stress across multiple systems. Oil degrades faster. Components operate closer to their limits. This process is driven by time and mileage, not abuse. Even engines that receive regular maintenance experience sensor drift. Because the engine still starts, idles, and drives without complaint, drivers assume nothing is wrong. That false reassurance allows inefficiency and wear to build uninterrupted. By the time performance noticeably changes, the engine has already been compensating for inaccurate information for years. But inaccurate data isn't the most destructive force inside an engine. Pressure is. At this point, most engines still feel fine. They start, they idle, they get you where you're going. And that's exactly why the damage we've been talking about is so easy to miss. Engines are incredibly good at adapting. They smooth over inefficiencies. They hide imbalance. They compensate long enough for problems to become familiar instead of alarming. What most drivers experience as normal aging is often an engine working harder just to feel the same. Slight airflow inaccuracies, fuel that doesn't burn as cleanly, pressure that isn't being relieved the way it should. None of these cause immediate failure. They quietly narrow the engine's safety margin. The goal here isn't to scare you or turn driving into a checklist. It's to help you understand what's actually happening beneath the surface, so small issues don't turn into expensive ones later. When you know why engines degrade, decisions become simpler and maintenance becomes preventative instead of reactive. Up to this point, everything we've covered lives in the background: sensors, corrections, quiet adjustments. This is how engines think their way around small problems without alerting the driver. But there's another layer. The computer can't smooth over forever. So far, we've been talking about how engines think. Now we need to talk about what engines feel. Because once physical forces inside the engine move out of balance, compensation stops being gentle, and the damage stops being subtle. Pressure. The damage you never see coming. Every time an engine fires, pressure is created. Most of that pressure does exactly what it's supposed to do. It drives the pistons, turns the crankshaft, and produces power. But a small portion always slips past the piston rings and enters the lower part of the engine. This isn't a defect. It's normal, and engines are designed to handle it. Trouble starts when that pressure can't escape the way it should. As internal pressure rises, it doesn't trigger a warning or create a sudden failure. It spreads quietly through the engine. Oil is pushed into places it was never meant to reach. Seals are stressed from the inside instead of the outside. Gaskets flex more than they were designed to. Oil circulation changes in subtle but important ways. Over time, pressure turns small weaknesses into visible problems. Seals that should last for years begin to weep. Gaskets fail earlier than expected. Oil leaks appear in places that seem unrelated. And because leaks are the first thing people notice, they're often blamed as the root problem. But leaks don't create pressure. Pressure creates leaks. Replacing a seal without correcting the internal imbalance is like drying the floor while the pipe is still leaking. The symptom disappears briefly, then returns somewhere else. This is why some engines seem to develop multiple leaks in a short period of time. The pressure problem was building long before the first drip ever showed up. Pressure-related damage doesn't feel dramatic. It feels confusing. One repair follows another. Each one seems reasonable on its own. But until pressure is managed correctly, the engine continues aging faster than it should. And there's one small component that decides whether pressure escapes safely or destroys everything: the overlooked valve that protects the entire engine. Every engine is designed with a way to manage internal pressure. During normal operation, a small amount of combustion gas slips past the piston rings. That gas has to go somewhere. When the pressure relief system is working correctly, those gases are safely routed out of the engine and burned again. Pressure stays balanced, moisture doesn't linger, oil stays cleaner for longer. When that system begins to fail, the change is subtle. Nothing breaks. No warning light appears. Pressure rises slowly inside the engine. Moisture that should be removed stays trapped. Fuel vapors mix with oil instead of being cleared out. Over time, that mixture thickens and begins forming sludge in areas oil was never meant to collect. The engine keeps running. The computer adapts. From the driver's seat, everything feels normal. That's what makes this problem so damaging. By the time symptoms appear, the imbalance has already been present for a long time. Those symptoms often seem unrelated. Oil leaks that return shortly after being repaired. Thick residue under caps. Idle that feels rough one day and fine the next. Each repair addresses what's visible, but the pressure causing the damage remains untouched. Once internal pressure is no longer controlled, wear accelerates. Oil breaks down faster. Seals harden earlier than expected. Bearings are exposed to contamination they were never designed to handle. What could have remained a slow, manageable issue begins compounding into multiple failures. Pressure doesn't destroy engines overnight. It shortens their lifespan quietly, pushing every system closer to its limits. Pressure isn't the only multiplier. Heat accelerates every mistake. Heat. The force that speeds up all damage. Engines are built to run hot. But they're engineered to operate within a narrow thermal balance. When temperatures drift slightly above that ideal range, not enough to trigger overheating, but enough to matter, the engine begins to age faster in ways that aren't obvious. Heat changes chemistry first. Fluids thin more quickly and lose their ability to protect. Additives that prevent wear and corrosion break down sooner than intended. Metal expands a little more than designed, altering clearances that are measured in thousandths of an inch. None of this causes an immediate problem. Instead, it quietly shortens the lifespan of everything involved. This is why the phrase "it never overheated" can be misleading. Overheating is a crisis, a clear warning event. Elevated operating heat is different. It's erosion. It accelerates wear without announcing itself. The engine continues to run smoothly while margins slowly shrink. Excess heat also magnifies other issues already present. Slight airflow restrictions create more load. Inaccurate fueling produces additional heat. Pressure imbalances stress seals and gaskets sooner. Heat doesn't cause these problems, but it makes every one of them worse, faster. Left unaddressed, this extra thermal stress compounds over time. Components that should last years begin aging early. Efficiency drops. Fluids degrade sooner. What once required minimal effort now demands more from the engine to produce the same result. Heat doesn't destroy engines on its own. It multiplies the damage from everything else. And the longer elevated temperatures persist, the faster the engine's safety margin disappears. And fluids don't just wear out by mileage, they age by exposure. Fluids that degrade even when the car feels fine. Fluids protect an engine through chemistry, not magic. Every fluid relies on carefully balanced additives to reduce friction, manage heat, and prevent corrosion. From the moment the engine runs, those additives begin doing their job and slowly wearing out. Heat breaks them down. Oxygen alters their structure. Moisture dilutes their effectiveness. This process is gradual, and almost none of it is noticeable while driving. That's why the idea of lifetime fluid creates confusion. Lifetime doesn't mean permanent protection. It means the fluid is expected to perform within design limits for a certain period under controlled conditions. Real-world driving rarely fits that model. Short trips, stop-and-go traffic, towing, heavy loads, and repeated heat cycles all accelerate chemical aging. Even fluids that look clean can already be providing less protection than intended. As fluids degrade, internal resistance increases. Lubrication films become thinner and less stable. Components have to work harder to move and rotate. That extra effort generates heat, and heat further speeds up fluid breakdown. The engine continues to operate smoothly, which makes the change easy to ignore. Efficiency drops first. Response softens next. Wear increases quietly in the background. This is why fluid condition matters more than mileage alone. Two vehicles with identical odometer readings can have very different internal health depending on how they were driven and the environments they experienced. Fluids don't age by distance alone. They age by exposure. And the way you drive matters just as much as what you change. Why short trips can be harder on engines than high mileage. Short trips seem harmless. The engine runs briefly, the drive feels easy, and very little mileage is added. Nothing sounds wrong. Nothing feels stressed. But engines don't judge wear by distance traveled. They respond to how long heat and airflow are allowed to stabilize internal conditions. When an engine doesn't reach full operating temperature, normal byproducts of combustion don't get cleared out. Moisture remains suspended inside the engine. Fuel vapors linger instead of fully burning away. Condensation settles in oil passages, the crankcase, and the exhaust system. All of this is expected during startup, but it's meant to be temporary. Sustained heat is what removes it. With repeated short trips, that cleanup never happens. The engine shuts down before oil can fully circulate and purge contaminants. Internal surfaces stay slightly damp. Acids remain active longer than they should. Residue that would normally evaporate or burn off begins to accumulate instead. Over time, this creates an internal environment that promotes deposits and accelerates contamination. This is why low-mileage engines can sometimes show more internal wear than engines with significantly higher mileage. The damage isn't loud or sudden. It's gradual. Day after day, small amounts of moisture and residue remain behind. The engine compensates, but the internal balance slowly shifts in the wrong direction. Driving habits shape engine health more than most people realize. An engine that regularly reaches and maintains proper operating temperature can stay cleaner, drier, and more stable than one that rarely does. Even if it's driven more often, mileage tells only part of the story. How an engine is used often matters more than how far it's traveled. Modern engines face another challenge that older designs never had. Quick reminder: if you want to catch engine issues early instead of repairing them late, subscribe here. The modern carbon problem engines were never built to handle. Modern engines are impressively efficient, but that efficiency came with a hidden cost. To meet emissions and fuel economy demands, many designs changed how fuel enters the engine. In these layouts, fuel no longer travels across certain intake surfaces during normal operation. That change removed a natural cleaning effect older engines relied on. As a result, oil vapors and combustion byproducts have a place to settle, and nothing to rinse them away. Over time, those vapors bake onto intake surfaces and valves. Carbon slowly accumulates in areas where airflow needs to remain smooth and predictable. The shape of the airflow path changes. Valves don't seal as cleanly. Air enters cylinders unevenly. This doesn't feel like a failure. Throttle response softens gradually. Acceleration feels a little less sharp. Fuel economy slips just enough to be explained away. Because the engine still runs smoothly and quietly, drivers rarely suspect internal buildup is changing how the engine breathes. Oil changes remain important, but they don't address this issue directly. Oil circulates through the engine's lower components, not the intake surfaces where carbon forms. That's why careful owners and neglected vehicles can experience the same problem. This isn't caused by skipping maintenance. It's a byproduct of modern engine design operating in real-world conditions. Carbon buildup has become a normal phase in the life of many modern engines, not a rare defect. And because it develops slowly and silently, performance often declines long before anyone realizes the reason. So how do mechanics actually bring engines back from all this? Fixing symptoms versus restoring engine health. Most engine repairs focus on what's visible. A leak shows up, so a seal gets replaced. Power feels weak, so a part gets swapped. The symptom disappears, and for a while the engine seems better. But in many cases, the underlying conditions that cause the problem never change. True restoration works differently. It looks at why the symptom appeared in the first place. A gasket didn't fail on its own. Pressure was already elevated. Power didn't fade because a single component aged. Airflow accuracy, fuel delivery, and combustion quality were already drifting. When repairs are done reactively, they often reset the surface problem without correcting the internal imbalance. That's why some engines cycle through repairs. One issue gets fixed, then another appears. Not because the engine is unreliable, but because stress is still present. Heat continues to accelerate wear. Contamination continues to build. Pressure still searches for the next weak point. Restoring engine health means rebalancing the systems that work together every second the engine runs. Airflow, fuel delivery, pressure control, lubrication, and temperature management. When those systems operate within their intended range, components last longer, and performance returns naturally. Engines that feel new again weren't rescued by a single dramatic repair. They improved because resistance was reduced across the system. Buildup was limited. Temperatures stabilized. Pressure had a controlled path to escape. That kind of recovery doesn't come from chasing symptoms. It comes from habits that reduce stress consistently over time. Which leads to the one habit that matters more than any single repair. Final thought. The simple habit that makes engines feel new again. Engines don't return to life because of one perfect repair. They recover when stress is reduced consistently. The habit that makes the biggest difference isn't complicated or dramatic. It's paying regular attention to how the engine breathes, moves heat, and relieves pressure before problems become permanent. That means addressing small changes early, letting the engine fully warm up when possible, keeping airflow and fluids clean enough to do their job properly, giving the engine a chance to clear moisture, burn cleanly, and operate within the conditions it was designed for. None of this promises miracles. It prevents slow damage. When engines feel new again, it's usually because resistance has been removed, not because something was added. The engine isn't being pushed harder, it's being allowed to work normally again. If learning how to protect your engine before repairs become necessary is useful to you, staying connected here will help you make sense of those early signs. Engines don't fail because they're old. They fail when small warnings are ignored long enough.